Howdy, everyone. When we left off last time, we were talking about forming null and alternative hypotheses, and we found that we had three different sets depending on whether a test was two-tailed, right-tailed, or left-tailed. These null and alternative hypotheses are going to define exactly what we're paying attention to when we actually try and run a hypothesis test. So, if you're interested in how to form these, or if you're not remembering quite how to form these, this is not what that's not what this video will cover. So you want to go back to the last video on forming null and alternative hypotheses, forming hypotheses to find that information. In this video, instead, we'll talk about how we draw conclusions, how we actually decide whether or not one hypothesis seems reasonable. Namely, we're going to decide whether or not to reject the null hypothesis. In other words, we're going to use evidence that we collect to decide if there is information we're getting that tells us the null hypothesis doesn't seem correct, doesn't seem reasonable. We never collect evidence that supports we never like say, oh yeah, no, we're accepting the null hypothesis. We simply fail. If we ever have something where our evidence is in line with the null, then what we're saying usually is that we fail to find evidence against the null hypothesis. The null hypothesis is the status quo, if you will, or leaving thing or just our baseline assumption or a representation of no change. So we have no need to find evidence for that. We begin by assuming we're everything we do assumes it's is based around assuming it's true until shown otherwise. So we never say things like we're going to accept the null hypothesis. That's an incorrect assessment of of the type of evidence that we're gathering. Um, we always are either going to reject the null hypothesis, meaning that we're preferring the alternative hypothesis, or we're going to fail to reject the null hypothesis, which means we stick with we stick with it, which means that essentially we're saying, yeah, there's nothing that says that we're not finding significant evidence saying that this is wrong. So remembering that, again, hypotheses are not things that are proven to be true or untrue. They are simply a statement that we try to, decide upon based on the weight of evidence. So let's talk about how we draw these conclusions. So we're going to have to decide whether or not we reject the null hypothesis based on how our test values react or relate to whatever baseline value we're working with. So let's say we're doing a left-tailed test, if our test values are significantly below what our baseline value is, then that might be something where we reject the null hypothesis because evidence is suggesting it's wrong. So here, for example, I instead show a right-tailed test. If a test value is far above a population mean and we're performing a right-tailed test, we reject the null hypothesis, which does mean, taking on the alternative hypothesis. That is reasonable. If it's not null, that only leaves alternative. So generally when we talk about like conclusions, we'll draw conclusions saying like, yeah, we find evidence, in support of the alternative hypothesis. That is a reasonable conclusion to draw. Anyway, aside, what happens here is that if we find enough evidence kind of supporting the alternative hypothesis, or more to the point, acting against the null hypothesis, then we reject the null and instead, conclude the alternative. And we'll see what exactly it's going to take for that to be enough evidence. That's what today's topic is about. So for the record, by the way, one of the reasons that a one-tailed test is sometimes a little sketchy is if we had these test values, our evidence that was significantly greater than whatever our population mean was, and we were doing a left-tailed test, we would not reject the null hypothesis because the evidence is not in the direction we care about. That's kind of why one-tailed tests are a bit strange. Is something different is happening and we don't care. And there are uses for that, as I think I said last time, but those uses are far less frequent than people seem to imply, in my opinion. So anyway, let's talk about how extreme is extreme enough to justify rejecting a null. So this is what I kind of hinted at this in the last video, and now we're going to look at it proper. The critical region is going to be the location where is going to be kind of a location where we say, hey, this is enough that we're going to reject the null hypothesis. If we see a value that's extreme enough, this is where we say extreme enough is happening. So so the idea here is that we might have a bell curve that represents the location of data points or the probability of finding data points, assuming the null hypothesis is true. So this bell curve is built assuming the null hypothesis is true. So the null hypothesis is the mean, or is based on the mean. So that means that whatever our null hypothesis is, whatever our value for k would be, the mean, which is just the dead center of this bell curve. So what happens here is the critical region, which is this region that's shaded, is the location where we say, like, hey, these values are far enough away from the mean that we don't think they happened by chance. Because what can happen here is we say, hey, values in here can happen by chance, but that might be a very small chance. A value in here, anywhere in the shaded region, might only have, for certain selections of alpha, which we'll talk about in a moment, might only have like a 5% chance of happening if this is the actual mean. So we say, maybe, oh, well, 5% only, and I'm getting values there. Well, then maybe it's, maybe that mean isn't proper because, I don't like that, I don't like that my values came out, or I don't think that my values would have come out, this extreme when there's, if the mean was actually where the null says it is. So instead we say, well, maybe the mean is, instead the conclusion we draw is, maybe we reject this mean and say that the mean should be somewhere else so that the values we got weren't so unlikely. So the idea here is that we're basing our test around the assumption that this is the true mean. And then if we get values that are really extreme, we say, well, maybe my best conclusion, maybe my best idea of what's happening is my initial assumption was wrong. And that would mean that we're rejecting the null. That would mean that we're saying the null seems wrong. Evidence suggests the null is incorrect. So this is, for example, this would be an example of a right-tailed test where we're saying, like, well, if we're getting data points, if we're getting test values that are unlikely to have happened by chance because they're too high, then we're saying, well, it was unlikely these happened by chance, so instead we're saying this isn't the mean. That we think the null hypothesis, the hypothesized mean in the null is false. And maybe the mean should be higher. And that would be a right-tailed test. That would be what's going on here. So this is the idea, is we're going to define a region that says, hey, this is too extreme. So it's got to be so the paradigm I've set, the starting assumption seems wrong. And if we look at these, this is a left-tailed test, where now the only thing I'm paying attention to is whether or not my values are too low. And this is a two-tailed test, where my values could be, where the values I'm looking for are, I'm going to say that my assumption for what my assumption in the null hypothesis is wrong, or I'm going to reject that assumption. I'm going to reject that hypothesis if my actual data values are too high or too low. So in this one, we kind of split the critical region in two. And you might notice in all these, there's this little symbol alpha. And this is the level of certainty I want to have. The level of significance is what we call it. And essentially the idea is the lower a value that alpha is, the more extreme my data points would have to be for me to say, oh, that's too far from the null hypothesis, so I'm going to reject the null. That's too far from the hypothesized mean. So the lower alpha is, the more extreme values would have to be for me to reject the null hypothesis. And what that means is, frankly, the more decisive your result, the more reputable your result will be. This is a really important part of test design, is picking a p-value that shows something significant if it's there, but or picking an alpha value, not a p-value. Sorry, we'll get to p-value. It's the same basic idea. I mean, but picking an alpha value that shows hey, like I can actually find a result that we say is extreme enough, or picking something where I say like, hey, I'm able to get this result, I'm able to find something extreme, but actually have it be obtainable, where if there is a difference, we'll find it. So we want something that's obtainable for something that we want something where if there is a difference, we'll detect it, but we also want something that's not too easy to obtain, so that we reject something we shouldn't have rejected. And finding that balance is really dependent on what you're testing, and really kind of up to a statistician to argue that they've picked a reasonable value for alpha. They've picked a reasonable baseline for what they would constitute extreme enough to reject a null hypothesis. If a statistician does this incorrectly, it can often result in their study not being taken seriously, or worse, if a statistician intentionally does this incorrectly. This is often kind of what's known as p-hacking, or this is part of what's known as p-hacking, where essentially you manipulate what you consider important, or you manipulate what you would call significantly different, or where you would say your level of significance begins to be obtained based on the data that you have. So you essentially say, oh yeah, I'm going to assume this is significant because it says what I want it to say. So picking your alpha value, picking your critical regions, so that it concludes something that you conclude a rejection when you should, but you don't reject something you shouldn't be rejecting, or that your case is still convincing, is an important thing to keep in mind. And fortunately, though these are arbitrary choices, if you remember the reading that I had you guys do, that I had you do before we went on spring break, our choices for alpha are originally somewhat arbitrary, and they are, but we've kind of hit a standard where we often pick levels of significance of 0.1, 0.05, and 0.01. In other words, if there was only a 10% chance of getting a 0.1 level of significance, would be if there's only a 10% chance of getting values as extreme as we got by chance, then that's when we'll conclude to reject the null hypothesis. That's when we'll decide the null hypothesis is evidence is suggesting it's not true. A 0.05 level of significance, which is, I would say, kind of at least in current in most experiments, you'll see this is kind of the gold standard, an alpha of 0.05. This is saying if there's a 5% chance that, if there's, you know, a 5% probability that that our data values occurred by chance, assuming that if the null hypothesis was correct and our data values simply occurred by chance, if that happens only 5% of the time, then that's when we'll reject our null hypothesis and say, well, that doesn't seem reasonable. And then 0.01 is the same thing, but with a 1% chance that the null hypothesis was correct and we got our values by chance. By just pure chance that you know, if we continued taking values, we would have ended up with the null. Alpha is realistically defined as the maximum probability, and that means that we might have a probability even more extreme than these, and that's fine, but it's the maximum probability of rejecting the null hypothesis when it's actually true. So in other words, if it's the probability that the results we got happened by chance when the null hypothesis was the mean that we began with, was the value that we're comparing things to, was k from, you know, was that the mean was indeed k from, you know, this slide. And sometimes that happens. Sometimes our values really did occur by chance, and we chose to reject the null hypothesis. We chose to decide the null hypothesis didn't seem true based on the evidence we had, even though it turns out it was. That can happen, and it's known as a type 1 error. So let's take a look at what errors are. So a type 1 error is when we reject the null hypothesis even though it turns out it's true, even though it's actually true. If we reject the null hypothesis and it turns out the null hypothesis, and it's actually that the null hypothesis is false, well, no problem, working as intended. If we don't reject the null hypothesis and you know, it turns out that the null hypothesis is indeed true, again, no problem, working as intended. You know, the experiment begins by assuming that, you know, we base our experiment around the assumption that the null is true to begin with. So if we're not rejecting it, then that assumption, you know, essentially continues. So no problem. And then if finally we don't reject the null hypothesis and it turns out that the null was actually false, that there actually is a difference, then this is known as a type 2 error, a beta error. So essentially what's happening here is we're failing to reject the null hypothesis even though we actually should have rejected it. You know, if we'd had access to perfect information, which obviously we will never have access to. So yeah, but we can liken this to a court, to a court of law. So you've probably heard the phrase innocent until proven guilty. This means that in the court of law, the base assumption that we begin with is that a defendant is innocent. And then we collect more and more evidence, and if eventually the evidence is so far from innocence that we say, you know, it's just not tenable to continue to assume that the defendant is innocent, that's when we reject the null hypothesis. We reject that the defendant is innocent, and that only leaves us with, you know, with the assumption that they're guilty. So that's the idea here, is that we can treat this exactly like it's a court case. We say, well, our initial assumption, our initial feeling is that the null hypothesis is true, that the defendant is innocent, and rejecting the null hypothesis would say, hey, evidence is suggesting that initial belief was erroneous. So evidence suggests that they aren't innocent, that we reject that, and that instead they're guilty. Rejecting So, and then not rejecting the null hypothesis, not rejecting innocence is essentially saying um, that we say, okay, well, we fail to find significant evidence saying that the defendant isn't innocent. So that's it. They're not convicted. And notice that this actually follows a little. This actually follows a little further. Rulings in the court are either we find the defendant guilty or we find the defendant not guilty. They are not we find the defendant innocent. Um, and that's a very important distinction. Once again, even in this even when we're looking at that, you can still see the same thing, is that the actual conclusions there are um, we reject, in other words, evidence suggests they're guilty, or we don't reject, which is we have no evidence. We have no significant evidence suggesting they're guilty. So we don't, there's no change. There's no change in the status quo. We don't find something different. So that's going to be the same in hypothesis testing. It's not that this is necessarily true. It's just that it's not that the null is necessarily true. We simply fail to find that it's false. Or we fail to find evidence that suggests it's false, I should say. Continuing with the courtroom metaphor here, if it turns out that the defendant was in fact guilty of whatever they were convicted of, if we reject the null hypothesis, that would mean we're finding them guilty when they are. So no problem, working as intended. And this is the thing that that's the last one we haven't talked about yet. Don't reject the null hypothesis, even though the null is with God information, even though the null is false. So don't reject null hypothesis, even though with all information we would find it was false. This just means that we didn't find enough evidence to reject it, even though we should, even though, if we had more evidence, maybe we would have. So in a courtroom case, it would again be this feeling of finding a defendant not guilty, even though it turns out they committed the crime. Now, think about a courtroom case. We're going to continue this metaphor because it's a really good one. In a courtroom case, which would be a more undesirable error? Would it be more undesirable to find a defendant guilty who is actually innocent of the crime, or would it be more undesirable to find a defendant not guilty when they actually were guilty? And I think most civilized people, I think most reasonable people would say that the far more distasteful result, the result it's far more important to avoid would be convicting an innocent man or woman, or convicting an innocent person. I think that would be the far more disastrous result of the two. And hypothesis testing and statistics feels the same way. We would much rather fail to find a result that we should have found than find a result we shouldn't have found. So type 1 errors are the ones that are generally considered far more deadly, because you're concluding something new. So you're shifting, you're shifting some paradigm, or concluding something new, or presenting this totally new idea when you shouldn't. And that type of misinformation is incredibly incredibly important to avoid. And many of the things where you hear about experiments gone wrong, or things where people really are using, people are really finding things that are awful, or just providing misinformation all over the place are examples of this, are examples of a type 1 error. You can, you can talk about, all sorts of different times when it would be really nice if someone found something that they should have found, but they failed to find, and that can be a problem. In terms of creating some standard to help get things done, that can be a problem. But it's far more deadly to provide information that you shouldn't be providing. So in general, we want our probability of a type 1 error to be low. That this is the one we can control, and this is the one that we control to be lower usually than our probability of a type 2 error. In general, it's very hard to compute a type 2 error correctly, directly, but the rule of thumb is increasing the probability of a type 1 error decreases the probability of a type 2 error, and vice versa. So let's go ahead and actually talk about finding places where we actually decide to reject the null hypothesis. So, let's move on from the death and destruction that was, this idea of, oh no, we've, convicted an innocent man in the courtroom, in the courtroom metaphor, or just, has provided all sorts of misinformation because, these things, do happen. We try and avoid them. And it is, a necessary risk. But we also need to make sure we can even conclude things at all. If we make it impossible to even draw a conclusion, that's not getting anywhere either. So let's talk about how we decide when evidence is enough to reject the null hypothesis. How do we decide on our how do we use our alpha to figure out what's enough to reject? And so here, once you have an alpha, once you've decided on your alpha or been given your alpha or what have you, let's talk about finding a critical value. Finding this value, this kind of line we've drawn that cuts off the place where I'm going to reject the null hypothesis from the place where I'm not going to reject it, from the place where data is, where the data I've collected says like, yeah, it's not, I'm not finding evidence of a significant difference. So here for a left-tailed test, we will take our alpha and find it in the center of the table. So when I talk about finding alpha in the center of the table, what I mean is whatever alpha we have, let's say that we have an alpha of let's say we have an alpha of 5%, of 0.05. Well, we're looking for 0.05 in the center of the table, which is right here between 0.0505 and 0.0495. It's negative 1.645 as a z-score, right? But the point is that the place we're looking for alpha is in the center of the table. I've seen a couple of you continue to look at z-scores. So, continue to be like, oh yeah, 0.05 would be, right here. No. We look for it as a probability or as an area. And then what we're going to do from there is we are then going to find the z-score for that probability. And it's going to be negative. So the z-score for that probability would be, as I said, let's go back to that. As I said, the z-score for something like alpha equals 0.05 would be right here, would be negative 1.645. And that negative z-score is our critical value. So that's going to be what tells me whether or not I'm far enough from my mean in order to reject the null hypothesis. Similarly, for a right-tailed test, we are going to find 1 minus alpha in the center of the z-table. That's going to be on the positive side of the table. And we're going to find that z-score. It's going to be positive. And that positive z-score is the critical value. So here, 1 minus alpha is what we're looking for. So again, let's go back to that table and we'll say like, oh, maybe I've got, let's say I've got an alpha of 0.01. So here that means we're going to be looking in the table for 1 minus 0.01, which is 0.9900. So that is right around here, right? This 0.9901 is about as close as we're going to get. So we might use a z-score of 2.33. So 2.33 is our critical value. So being beyond that critical value would be when we reject the null hypothesis. And that's going to be our rule of thumb, is if you're beyond a critical value, that's when you reject, because that's what's going to put you in, being beyond a critical value is what's going to put you in, this region, in the shaded region where we reject the null hypothesis. Finally, with a two-tailed test, you're going to start by dividing alpha by 2. So if alpha were 0.05, you would make it, you would look for 0.025. You're going to find alpha over 2 in the center of the z-table. Easiest to do this on the negative side. You could also find 1 minus alpha over 2 in the center of the z-table on the positive side, but it's just easier on the negative side. And then you're going to find the z-score for that probability. So we talked about alpha of 0.05, so we look for 0.025, which is right here. And now we find the z-score for this, which is negative 1.96. Almost like we've seen that particular z-score before. And so what we do is we take that, and both the positive and negative versions of that z-score are critical values. This should remind you a lot of what we were doing when we found confidence intervals. And that's not accidental. In point of fact, if we look at this two-tailed test, the confidence interval for a 95% confidence level would exactly be the non-critical region. And that's exactly the non-critical region. So you can think of hypothesis testing as exactly the opposite of finding a confidence interval. So we're rejecting, essentially the idea is we're rejecting the null hypothesis when the confidence interval when we are not in the confidence interval for the null hypothesis. So that should make a lot of sense. Where, if we were 95% sure that we should be in here and we're not, well, maybe that means wrong. So an example of this, let's just show kind of finding examples. We already talked about this one. If we have an alpha of 0.01, you can find the z-score for that critical value by finding the z-score for an area of 0.99, which we saw was 2.33. And we saw this one too. Consider a two-tailed test, alpha equals 0.05, find the z-score for the critical values. So a two-tailed test is symmetric, so we look for an area of 0.025 on either side. So again, we got positive 1.96 and negative 1.96. You can also, for the record, find a right-tailed test by simply finding the z-score for alpha directly on the negative side of the table and then just saying, oh, but I want the positive score, because the normal distribution z-scores are symmetric. So, concluding this, once again, if your test is right-tailed, there's one critical value and it's positive. If it's left-tailed, there's one critical value and it's negative. If your test is two-tailed, you'll have two critical values, which are going to be symmetric, and one's positive and one's negative, and they are going to be built from an alpha that's, half of your starting alpha. And let's just, put this all together into a single example here. I started the slideshow by talking about a superintendent who wants to test if his school was above average on the SAT. He had we saw that he had a mean of 1100, and the population mean was 1050. So he wants to see if his mean of 1100 represents a significant difference from 1050, represents something that he can adequately say that he can adequately conclude, at least based on weight of evidence, didn't happen by chance, that his school is actually noticeably better. And this might be one of those rare occasions, depending on depending on the use for this information, this might be one of those rare occasions where I would say a one-tailed test might be reasonable. If he's looking to say like, hey, other schools might consider, like looking at my school's example, um, if that's the conclusion that he's looking to draw, maybe a one-tailed, maybe it's reasonable to just say, well, if it turns out I'm wrong and it was supposed to be below, and we already have the information that says, no, but if before collecting any of this, he said, it's something where he says, like, yeah, if it turns out I'm wrong and my school is actually worse, or has data points below the population mean, well, I just wouldn't take action. Um, where I wouldn't set up my school as like a, hey, I want to show what I'm doing here. um that might be an occasion where a one-tailed test is correct, because having being wrong side of your test wouldn't actually affect, wouldn't actually be any different than just failing to reject the null hypothesis in a more normal way. So there's a rare occasion where I might say a one-tailed test is reasonable. But let's add some going back to this, let's add some info and say he sampled 64 students and had a standard deviation of 160, and decided he wanted to test this using an alpha of 0.05. So it's a right-tailed test. So when we're looking for a right-tailed test with alpha equals 0.05, what we're really looking for is we're really looking for an alpha, for kind of 0.95 in the z-table, right? And we're going to see what z-score corresponds to that. So if we go to this table, we find 0.95, which is right in here. And so it's a z-score of 1.645. Once again, you could have also just found 0.05 directly and got negative 1.645 and just said, yeah, but it's right-tailed, so it's positive. In any case, a z-score of 1.645. And that's going to be our critical value. And let's, quickly just, I skipped over this, but really shouldn't have. It's a right-tailed test because we are caring about an increase specifically. He wants to know if the school is above average. He doesn't care if it's below average. So the null hypothesis should be that the mean is less than or equal to 1050. The alternative should be the mean is above 1050. So what we're going to do now is actually find the z-score for our sample mean, and we're going to compare that to the critical value. The z-score is sample mean minus population mean minus the assumed population mean, I should say, minus the null hypothesis mean, over standard deviation divided by root n. This is just your central limit theorem z-score. No surprises here. Which this is going to work out to 2.5. Feel free to check my math, but it's 2.5. And since z-test equals 2.5, this is beyond our critical value of 1.645, so we reject the null hypothesis. So we're going to say that evidence suggests the superintendent school did indeed have higher SAT scores. And this evidence suggests is an important line, right? It's notice, it's important that we say, it's important that we note that that our conclusion is based off evidence, not absolute fact, because everything we do here is based, everything we're going to do in this course is based off evidence, and we we need at least to reference that fact. So let's just go ahead and show kind of what was going on here. Here's our bell curve. And this is just our x-axis, whatever. And so, this might be our critical region, right? This is our alpha, equals 0.05. And the shaded area that I've got here has an area of 0.05. And we saw that right here, this was my critical value, which was a z-score of 1.645. And what we ended up finding here was we found a test value of 2.5, which might have been like right around here. which had a z-score of, 2.5. If we want, we can, call it z sub t, z sub like test if we want to call it that. But we got a test value of 2.5. Gonna just get rid of that because it looks terrible. So what happens here is this test value is in our critical region. So this is saying, hey, this is extreme enough that my assumed mean doesn't seem reasonable. So this is why we're rejecting the null hypothesis. More about this in a future slideshow when we really get into like practicing hypothesis testing for the mean. But for now, that's about all I wanted to do. Mainly, this is about finding those types of errors, talking about finding what critical values are, just dealing with what it is that alpha represents. So yeah, until next time.